Okay, so this is a little bit of extra feedback for the evaluative task that you've done from June 2012, May 2013 on identifying a group 2 carbonate. So if we begin with question 1, it asks us to calculate the mass of the carbonate used. This is a simple subtraction. You have the mass of the weighing bottle and the carbonate and the mass of the empty weighing bottle, so the difference between the two must be the mass of carbonate that you actually used. If we have a look at B, calculate the amount in moles of carbon dioxide collected in the measuring cylinder, you're actually given information in the question on the quantity of gas that you've got, and you're told that it's 228 centimetre cubed. Now, because we've got a gas, CO2, we need to go back to the equation V equals N times 24 if it's decimetres cubed, or 24,000 if it's centimetres cubed. And if N equals V over 24,000, because we're working in centimetres cubed, that gives us 228 over 24,000, which equals 0.0095 for our number of moles. Because the stoichiometry in the equation is 1:1, the number of moles of CO2 is equal to the number of moles of carbonate, XCO3, and therefore the number of moles of carbonate is also 0.0095. If we have a look then at D, so D is asking us to deduce the formula of the carbonate, calculate the molar mass of the carbonate to 3 significant figures, and hence deduce the formula of the carbonate. Where we would go from here is looking at the fact that molar mass is equal to mass divided by number of moles. We know the mass of the carbonate because we calculate it in question 1a, 0.801. We divide by the number of moles, N. We know that that's the number of moles because we just figured that out in part C. And that gives us a value of 84.3. An answer of 84 is not acceptable for a mark on this occasion because it does ask specifically in the question for 3 significant figures. Moving on to the second part of D, where it asks us to calculate or to figure out the formula for the carbonate. If we take 84.3 as our molar mass of the whole carbonate, we subtract the values that represent the carbonate part, the CO3, which is equivalent to 60, and we're left with 24.3. Therefore, the metal that we are looking at must be magnesium. Now, if you wrote magnesium, you wouldn't get a mark. If you wrote Mg2+, you wouldn't get a mark because the question states the formula for the carbonate, as in the whole carbonate. So you have to have MgCO3 to qualify to get the mark on that question. The next question is a question on errors, and these questions are getting more and more frequent. Calculate the percentage error in the volume of carbon dioxide measured in this particular experiment. Now, the volume of carbon dioxide that we measured was 228 centimetres cubed. So we have to look at what our error is. It's plus or minus 1 centimetre cubed. It gives us that information in the question. And when we're calculating errors, it's 1, the actual value that's stated as the error, so in this case 1, divided by the quantity that you've measured, which we looked earlier was 228 centimetres cubed, and then multiply by 100 to convert it into a percentage. This gives us 0.44%. If you rounded on this occasion, then that was fine. They did allow you to have the mark. The next question is asking us to suggest one procedural error that would have resulted in student 2 obtaining a molar mass greater than that of student 1. Now, the straightforward answer to this is that the gas may have escaped. And if you look at the apparatus that they have used, the likelihood for that, and a little bit of extension for this, is that the student didn't replace the bung quickly enough, and therefore some of the gas escaped before we did the measuring. The next question, checking the practical, the student realised they've used more nitric acid than they should have done, and thinking about whether or not this is going to have an impact. What you need to do here is consider the quantities in terms of moles. Now, if we look at the moles of carbonate that we used, we know that it's 0.0095. We've calculated that earlier on. If we look at the moles of acid we use, if we're using 0.2 molar and we are using 110 centimetres cubed, then we find that the number of moles we use is 0.022. This is in excess of the moles of carbonate. If we only use 100, we end up with 0.02. This is still in excess of the number of moles of carbonate, which means that when all of the carbonate has reacted, we will still have some acid left over. Therefore, on this occasion, using a wrong volume of acid is not going to have any impact on the experiment as such. The next question is asking us, state and explain how use of the same mass of powdered carbonate would affect the rate of reaction and the volume of gas produced in the reaction. Now, as you can see, this student has written the faster the rate of reaction due to the surface area being bigger. So a larger surface area is the reason that we have a faster rate of reaction. Now, the volume of gas produced in the reaction is actually exactly the same. And it's going to be the same because the quantity of the reactants in both experiments is exactly the same. If you have the same amount of reactants, you get the same amount of products. Next question starts to get a little bit more complicated and is asking us to include state symbols in our written equation. Most students forget to include their state symbols. So you need your S solid for your carbonate, your S solid for your oxide that's produced, and then your G gas for your carbon dioxide that's produced. The next question is somewhere that student starts to struggle. Using the results of student 3, calculate the molar mass of the group 2 carbonate and give your answer to the nearest whole number. Now, what we would need to do in this case wrong sheet. There we go. We can't calculate the number of moles of carbonate because we don't have enough information, but we do have enough information to figure out the number of moles of carbon dioxide. So if we take the mass of carbon dioxide and we calculate that from the table as being 0.242, we find the molar mass of carbon dioxide, which is 44 from our periodic table, and we can calculate the number of moles of CO2. The number of moles of CO2 is equal to the number of moles of MCO3 because of stoichiometry, so both of them are 0.0055. And if we rearrange our standard equation n equals m over m, we find that molar mass is equal to mass divided by moles, and therefore we have 0.451 over the number of moles we found earlier to give us a molar mass of 82. The next question is asking us about errors. The mass of the carbonate measured by student 3 has a greater percentage error than that of student 1, and looking at why this is. Now, this is quite simply because one of the students weighed a larger mass or had a larger mass. Think about it in terms of actual numbers. If I have a 0.5 error, and I've just used this number to illustrate a point, calculating an error is the error divided by the quantity used. If we have a large quantity multiplied by 100, we end up with 5%. If we have a small quantity and the error is still the same, 0.5, we end up with a large percentage error. So the larger the mass that you use, the smaller the error that you have, and vice versa. The last question is quite a long explanation. When student 3 heated the test tube, some of the solid was lost. What would the effect on the calculated molar mass be? Now, this isn't as straightforward as it seems, and I need to use numbers to try and illustrate this when I'm figuring these things out for myself. Now, we figured out earlier that we had lost 0.242 grams of CO2. If we convert this into moles, we figured out that was 0.0055, and therefore our molar mass was 82. We've already done that. If we consider that some of the solid had actually been lost, then we think that we have lost a lot more CO2. So if we're losing some solid, we would then end up with a loss potentially of 0.342. And again, I'm using this number to illustrate a point. This is made up of CO2 and the solid that we lost, but we don't actually know that that's solid. We think it's all CO2. So when we work through our calculation, the number of moles of CO2 using this number would then equate to 0.0077. Now, this is greater than it really is. We think that we have more moles of CO2 than we actually have, and that's what would get us our first marking point. If we work through and process, the moles of CO3, because the stoichiometry is equal to the CO2, Therefore, the molar mass of the whole carbonate is mass divided by number of moles. We know that our number of moles is now 0.0077, even though it actually isn't. And using the same mass as we did earlier, 0.451, dividing through, we end up with the number 58. This number, as you can see, is significantly lower than the calculated value we had earlier. So the marking points for this come from two things. Number one, by stating that the moles of CO2 that we think that we've lost is actually greater than it really is. And this leads to a decreased value for our molar mass. It's less than it really is. So that is the summary of Evaluative Task 2, feedback.